So that sets the scale of the universe, how big it is and how old it is. But now the question is which of those cosmological model curves it follows. And that requires us to measure other cosmological parameters. And there's two basic paths to this, so-called standard candles and standard rulers. Just to refresh your memory, the idea here is you want to find out on which of these different R of t curves do we live. And since you cannot see in the future, all you can do is look along our past light cone and measuring the redshift gets you the scale factor stretch, and then somehow you need to figure out the distance to things that you're looking at. And that determines which model we have been writing so far. It's a fairly well-established approach, and there are different ways in which we can do this. Again, to remind you, all of these tests consist of inverting the expansion diagram, R of t, into, well, R of t becomes redshift, and t becomes actually the distance to something, look back time, and which is fine. So in this case, the beginning is at the Big Bang, but once you go in the redshift test for Big Bang is at the redshift of infinity, and today is the redshift of 0. And less than 0 is the future, right? Generic behavior that you expect to find is that in the models where there is more deceleration that slows down the expansion, more gravity, higher density, and or negative cosmological constant, those models will be smaller at any given time, and therefore things will look brighter, they would look bigger, but the volumes will be smaller. And the opposite of that is for low density models or models in which cosmological constant accelerates the expansion. Objects in those will be further away, they will look smaller, they'll look dimmer, but they'll be more up, it's larger volume. Now, it turns out that we actually don't measure absolute distances to anything. Even SZ clusters, there is some model dependence. But that's okay, because the scale of the whole thing is outsourced to measurement of the Hubble constant. All we need to do is consistent measurements of relative distances to some set of objects. And since it's all log-log plot, you can shift them, so that's fine. And so all you need to do is measure relative distances. And the way we do this is either using relativistic equivalent of inverse square law for sources of standard brightness, standard candles, or of angular diameter versus linear test. Hubble diagram, as you recall, is now not just measure of expansion rate, but once you know the slope, the curvature of Hubble diagram at high redshifts will start telling you about geometry of the universe at large scales. And so that requires sources that you think do not change their brightness, well, rather, at some instant are always the same brightness. And angular diameter test requires you to know absolute size of something on the sky. Source counts are possible because that measures the volume, but you need to have some tracer population that you can see and observe, and you have to be assured that they're actually not changing by number density, and there is no such thing. Now, you could, in principle, also measure ages of galaxies by fitting their stellar populations, but there are so many parameters involved in that, that's not very practical. Now, completely independent of these distant measurements, you can measure density locally, just from dynamics, large-scale structure dynamics, where cosmological effects are not so important, but the overall mean density tells you how much mass is there, and that can tell you what the matter density is. If you can then measure Hubble constant and age independently, you can constrain combinations of the others. So all of that has been tried. Things to be aware here is that there is always a selection effect. You're always using some population of tracers, like galaxies or supernovae or clusters or something. And there is always limit to your measurements in flux or in angular resolution. You're always going to be missing a faintest end of the population, and you don't know what you're missing. And so what you observe is a biased set at high redshifts, and so you have to do something to figure out what that must be. Otherwise, you'll be fitting a wrong model, because you're only fitting to those sources that you can see, that you can detect. And this is the generic behavior now you expect for Hubble diagram, as I already mentioned. So there are different things that have been tried. Originally, people tried to use brightest cluster galaxies. Well, since galaxies are made of stars and they merge, galaxies are not standard candles. They evolve in time. So that doomed that approach. Uncounted nights of Palomar 200-inch time have been spent trying to do this. In fact, people said, well, they built 200-inch to measure Q0, acceleration parameter, because they already knew Hubble constant to 10%, neither of which was the case. It turns out that now supernovae of type 1a can be used, and maybe even gamma ray bursts. But before we get into that, let's find out if the universe is actually expanding. I think this is a stupid question, but yeah, it's a legit question. We think the universe is expanding, that's what causes Hubble diagram to appear. But you could have a model in which there's so-called tired light model, in which photons somehow lose energy. The universe is stationary, but the further away photons travel, less energy they get. That's going to look exactly the same. So how can you tell? And there are two typical tests. One is about surface brightness, so-called Tolman test, and the other one is about time dilation in supernova light curves. The way Tolman test works is that surface brightness, which is flux per unit solid angle, is the same thing as luminosity per area, does not depend on distance in Euclidean space, right? But see, there is a ratio of square of angular diameter distance and luminosity distance. Since they depend on redshift in a different way, when you do this, you find out that relative to the Euclidean case, surface brightness in an expanding relativistic universe goes down as 1 plus redshift to the 4th power. And that's a unique prediction, right? So how can you find something that has a standard surface brightness? Well, this is where our scaling relations come in. And you can express them as surface brightness versus something else. And you look at two clusters and see how much shift there is. And that tells you how much decrement there was due to the expansion. So when it was done for elliptical galaxies in clusters, there is the result. That's amazingly good fit. So we think the universe does expand. The other test is using supernovae as clocks that make one tick. And here what's shown on the top is a whole bunch of supernova light curves centered on peak brightness. And in one case is all of them, the other is bin in magnitude. And then if you don't apply any corrections, see there is a law of spread. Now, if you correct each one of those to be stretched by 1 plus redshift factor because clocks tick slower there, suddenly they line up beautifully on a light curve. So this can be done in the opposite sense, and that too provides a clear demonstration that yes, the universe is expanding.